Okay, so I'd like to introduce you to the concept of a probability mass function. In order to properly explain this to you, I'm going to go ahead and add on another dartboard for a moment. Now, as we said, we can think of the set of all possible positions where you can land a dart on this dartboard. Now, I want you to imagine somebody who's been playing darts for a really long time, and we go ahead and record how many times he scores each possible shot. After letting them play for a long time, we can come up with the probabilities of every possible value. Now what this tells us is that this particular player gets a 3 31% of the time. So 31% of the time, their shot will land somewhere in here. We can also say that they get a 1 16% of the time. So 16% of the time, their shot lands somewhere in here. Now if we bring on an axis, we can actually talk about particular shots that this player could score. So I can go ahead and mark a few positions where this player ends up scoring a 3. As we already know, a random variable is just a function from these elements in this sample space directly to some real number, which in this case is any number between 0 to 5. Let me get rid of the shots in the bottom right hand corner, and I'll just go ahead and keep some of the shots that I need for now. I'm going to call this particular shot L, and it's at the position 2 minus 1, as you can see. Now as we can see, this shot L maps to a value of 3. We say that the function that maps some random element in your sample space directly to a real number is called a random variable. In this particular case, the random variable that we're using is called capital V. Here we can see that if we apply this point 2 minus 1 directly to the function capital V, we should get 3, as I'm about to show. This function just looks at your coordinate and decides what value it's in. As we've already stated, if you use this random variable, there's lots of points that map to the number 3. If we wanted to, we can actually form a set of all the possible points that map to the number 3, which I'll go ahead and do now. As we stated in a previous lesson, we can call this set the set capital V equals 3. Now that we have a set, we know that we can use a probability function to work out this actual probability. So I'll go ahead and draw on a number line to show you this probability. Now I can go ahead and feed the set directly to the probability function to map it to its actual probability. If we wanted to write this explicitly, we can just say that the probability of capital V equals 3 is just 0.31%. It's a bit complicated to use this. We're taking all the values in our sample space that map to the exact same output, forming a set out of them, and then mapping that set through the probability function. It would really be a lot simpler if we could just go ahead and map this value directly to its probability, which is what we will try to do now. We define a new function called the probability mass function that actually does exactly what we want. It takes this value here, and it just maps it directly to the probability that we're after. You have to be a little bit careful though, because this function takes a real number as an output and not a set anymore. We can label the probability mass function with a p, where the subscript is the random variable. We can therefore just sub in the value that the random variable takes to get the probability, as I'll show now. As you can see, doing this is just the same as doing this. So you could make a set out of all the values that give you a 3, and then go directly to its probability, or you can go ahead and take this value and just go straight to the probability using the PMF. So therefore we can write that this is the same as this. But since this is general, we can go ahead and replace the 3's for any value v. The probability mass function still has to follow all the rules of probability. So if you had the probability of getting a 0, 1, 2, 3, 4, or 5, you should still get a probability of 1. You can verify this by just looking at the probabilities in the table. A really common thing that we like to do is to draw a graph of the probability mass function, which we call a probability distribution. Let me go ahead and show you one right now. These are all the same probabilities from before, and here's a graph that we can populate. On the x-axis, we're going to have the value of the random variable, and on the y-axis, we're just going to have the output of the probability mass function. Now from the table, we can just see that p0 is 10%, so we can go ahead and graph this on the graph below. We can go ahead and repeat this for all of the other values as well. Now you'll notice that the PMF just isn't defined for numbers like 3.5. That's because this is a discrete random variable, as we've said in the past. Using this probability distribution, we can come to some pretty easy conclusions. We can say that this person is most likely to hit a 3. We can also see that they get a 1 and a 4 about as often as each other. And we could use this to really analyze this person's game as much as we like. Now it's all well and good to be able to deal with discrete random variables, but it might be nice to think about what might happen if we have continuous ones instead. So let's go back to the graph above and try to investigate that as well. I'm going to go ahead and get rid of all the information related to this value v. So the next random variable I'd like to discuss is a continuous one. So let's look at one that maps any coordinate to its x value. For example, let's choose a random point. You can see that this point is just the point -1, 4. Let's label the axis of the output of the random variable. As you can see, the x-coordinate of this position is just -1, so let's go ahead and map that directly. We say that the random variable in charge of this mapping is the random variable x. So therefore, x of -1, 4 is just -1, since the x-coordinate of -1, 4 is just -1. Now we might like to think of all the possible places where a dart could hit, where the x-coordinate also equals -1. Let's go ahead and draw them on directly. As you can see, these form a set, which is just a line in this case. If you wanted to, how likely are you to throw a dart that lands exactly on this line without being even a little tiny bit off? I hope you realize that if you zoom in, any shot you take is going to be a little bit off, even if you feel like it's really close. We know that this set is just the set where capital X equals -1. And as we'd expect, the probability of this set should be pretty much 0, which we can write like this. As a result, we would expect that the probability mass function should also return 0. Therefore, when we're dealing with continuous sets, it doesn't really make sense to take exact values like we did here. What we'll do instead is we'd opt to take a range of values. Let me show you. Maybe I'd like to find the probability of landing the dart somewhere in the range of -3 to 1. We can use these to construct a set directly on the dartboard as well. We can name this set capital X is between -3 and 1, which we can write like this. As you can imagine, any point inside this set will always map somewhere into the range of random variables that we want to get. But this is pretty messy, so let's just get rid of these arrows for now. I'll only draw the arrow for that purple coordinate that we have on the page. Now if we understand this properly, I want you to imagine what the probability of getting this area is. As you can imagine, it's not 0 anymore. I want you to imagine that we sat down and watched this player throw thousands and thousands of shots, and we made a heat map of all the places where their throws landed. Now I want you to think of this whole sample space almost like it's a cake, where different parts of the cake are heavier than others. If you were to cut out this slice of the cake, then you could easily weigh it on a scale. This is pretty much what we're doing when we're finding the probability of a set. Let's pretend we counted up all the throws and we found that about 28% of all the shots landed somewhere in this region. Therefore, the probability function would map this set to 28%. However, since the probability mass function just takes single numbers at a time, unlike this function which takes sets, we need to come up with something else to actually help us map this whole region directly to here. We'll discuss this in a future lesson.